The belief engine, Bayes' theorem and the logic of inference. From Thomas Bayes' 18th century geometric insight to the foundational algorithm behind modern machine learning. This video explains the full framework with real numbers, priors, likelihoods, denominators, and posteriors worked step by step. Theory and calculation today, interactive tools in a follow-up. The paradigm shift, forward versus inverse probability. Classical frequentist thinking runs cause to effect. If the coin is fair, what is the chance of heads? Bayesian thinking runs effect to cause. If symptoms appear, which disease is most likely? Bayes reversed the logic. Probability becomes a dynamic tool for revising belief when new evidence arrives, not a static label for known systems. The mechanical engine of logic. 4 components drive every update. Prior belief P of H, your starting position before new data. Likelihood P of D given H, how probable the evidence is if the hypothesis is true. Marginal evidence P of D, the normalizing gear that sums every way the data could have appeared. Posterior P of H given D, your updated belief after observing the data. Learning equals belief revision. Today's posterior becomes tomorrow's prior. 3 foundational rules scaffold coherent probability. The addition rule, for mutually exclusive outcomes, P of A or B equals P of A plus P of B. The complement rule, P of not A equals 1 minus P of A. The multiplication rule, joint probability P of A and B equals P of A times P of B given A. These rules partition, contrast, and link events without logical gaps, the plumbing that makes Bayes' formula derivable, not magical. The denominator net catches all alternate realities. Total evidence P of D equals true positives plus false positives. P of D given H times P of H plus P of D given not H times P of not H true positives mean the hypothesis is true and you still see the evidence. False positives mean the hypothesis is false, but the evidence appears anyway. The denominator normalizes the posterior so rare events do not break the math. Natural frequencies make the invisible visible. Take 1,000 people. Only one has the disease, prevalence 1 in 1,000. The test catches that one person as a true positive. Among 999 healthy people, roughly 1% false positives gives 10 false alarms. Total positive tests, 11. Only one of those 11 actually has the disease. 1 divided by 11 is about 9%, not 99%. Counting people instead of decimals exposes the base rate instantly. The 5-step diagnostic dashboard. Step 1, define H as hypothesis and D as data. Step 2, map knowns, prior P of H, complement P of not H, likelihood P of D given H, false positive rate P of D given not H. Step 3. Build denominator P of D by adding every mutually exclusive path to the evidence. Step 4. Divide true positives by total positives. Step 5. Interpret posterior P of H given D in plain English. Most mistakes happen at Step 3, forgetting false positives or alternate causes. Solved example 1, the rare disease anomaly. Context, test is 99% accurate with 1% false positives. Disease rate is 1 in 1,000. Step 1, H equals has disease, D equals tests positive. Step 2, P of H equals 0.001. P of not H equals 0.999. P of D given H equals 0.99. P of D given not H equals 0.01. Step 3, denominator equals 0.99 times 0.001 plus 0.01 times 0.999. That is 0.00099 plus 0.00999, totaling 0.01098. Step 4, posterior equals 0.00099 divided by 0.01098. Step 5, result is about 9.01%. 99% accurate, does not mean a 99% chance of disease when the base rate is extreme. Same test, different base rate. Disease prevalence is now 1 in 100, instead of 1 in 1,000. Knowns, P of H equals 0.01, P of not H equals 0.99, likelihoods unchanged at 0.99 and 0.01. Denominator, 0.99 times 0.0, 1 plus 0.0, 1 times 0.99 equals 0.0099 plus 0.0099, totaling 0.0198. Posterior, 0.0099 divided by 0.0198 equals exactly 1/2. 50% chance of disease. Same evidence, same test accuracy, radically different answer because context changed. Bayes anchors evidence to reality and defeats the base rate fallacy. The prosecutor's fallacy reveres the conditional. Left side, P of evidence given innocent, the false positive rate. How likely is a coincidental match if the person is innocent? Right side, P of innocent given evidence, the posterior. That requires Bayes' theorem and the crime's base rate. Mistaking the left for the right is lethal. A low chance that an innocent person matches the evidence does not imply a low chance that a person who matches is innocent. Solved example 2, the corporate hire. 3 candidates A, B, and C apply in ratio 1 to 2 to 4, so priors are 1/7, 2/7, and 4/7. Profit improvement probabilities are 0.8, 0.5, and 0.3. Solved example 3, the 3 urns. Urn 1 has 3 white and 2 black balls. Urn 2 has 2 white and 3 black. Urn 3 has 4 white and 1 black. Pick an urn at random, draw white. Priors 1/3 each. Likelihoods 3/5, 2/5, and 4/5. Denominator 1/3 times 3/5 is 3/15, plus 1/3 times 2/5 is 2/15, plus 1/3 times 4/5 is 4/15, sum 9/15. Posterior for urn 3. 4/15 divided by 9/15 equals 4/9, about 44.4%. The urn with the most white balls is favored, but not certain. Bayes quantifies the remaining doubt. Expressing likelihoods, odds and expected value. Odds equal P of a divided by P of not A. Conviction relative to its complement, not isolation probability. Posterior odds compare competing hypotheses directly. Expected value equals the sum of each outcome times its probability, weighting reward by likelihood. Unlike maximax or minimax heuristics, expected value uses the full distribution to guide rational decisions under uncertainty. Accumulating evidence with the binomial model. When trials are independent and repeated, count successes instead of tracking every sequence. Formula, C of n comma k times p to the k times 1 minus p to the n minus kc of n comma k counts, ways to get k successes in n trials. As n grows from 10 to 30 to 50, the distribution narrows around the mean, the law of large numbers. More data concentrates belief. Scaling the engine into modern AI. Naive Bayes classifiers parse text and filter spam under conditional independence. Bayesian networks propagate cause and effect through structured dependencies. Thompson sampling balances exploration versus exploitation in recommendations. Bayesian optimization tunes hyperparameters efficiently without brute forcing every combination. 18th century inverse probability now powers autonomous learning systems. Solved example 4, naive Bayes text classification. Email contains offer and win. Is it spam? Prior, 40% spam, 60% not spam. Likelihoods, P of offer given spam 0.5, P of win given spam 0.4, P of offer given not 0.1, P of win given not 0.05. Spam score, 0.4 times 0.5 times 0.4 equals 0.080. Not spam score, 0.6 times 0.1 times 0.05 equals 0.003. Denominator: 0.080 plus 0.003 equals 0.083. Posterior: 0.080 divided by 0.083 equals about 96.4% spam. Two suspicious words swing a moderate prior into near certainty. Bayesian networks and the decision tree. Disease causes symptoms. Symptoms drive test results. Edges apply the multiplication rule for joint probabilities along paths. Leaf nodes sum via the addition rule to build marginal denominators. Networks map dependencies explicitly so systems infer upstream causes. Disease by chaining conditionals backward from downstream observations like test results. Thompson sampling, the algorithm of learning. 3-slot machines start with wide flat belief curves, weak priors, high uncertainty. The algorithm draws a random sample from each posterior and picks the highest. After rewards or failures, curves shift and narrow. Posterior concentrates around true payout. Exploration tests uncertain options. Exploitation chooses the likely best. Bayes updates beliefs after every poll. Bayesian optimization and A/B testing. Traditional p-values give a binary significant or not. Bayes returns a full posterior distribution. Model selection with the Bayesian information criterion. BIC balances explanatory power against complexity penalty, parameter count. Derived from a Bayesian approximation to marginal likelihood, it favors models that fit data with the fewest parameters. Statistically likely and functionally economical, the scale tips toward simplicity unless extra parameters earn their keep. The unbreakable contract between data and belief. Bayes' theorem is not opinion. It follows from the rules of probability. Priors are not arbitrary flaws. They are essential baselines that regularize belief when data is scarce. Failing to update leads to base rate fallacies, misdiagnoses, and biased forecasts. What began as a geometric billiard table thought experiment is now the defining framework for reasoning under uncertainty. Bayes remains the first and ultimate algorithm of learning. That is the belief engine. Bayes' theorem from philosophy through full numerical examples to modern machine learning. In the next video, I will show live tools, calculators, simulators, and code. This episode walked every calculation on purpose. Subscribe to Life of Geeks, comment Bayes for updates, and scan the QR code for the channel.